All right, so today, hopefully we can get to the unreasonable effectiveness of mathematics in large-scale deep learning. But for the time being, let's time travel back to 1969. And Kennedy says, oh, let's go to the moon. And if you're on the other side of the Iron Curtain, Stalin says something similar. But unfortunately, something happened with your time machine. And the time machine got rid of Newton in your timeline. So you had to launch a rocket to the moon without knowing what gravity is and what the numbers are. So the best way you can do this is just to try and error. So, well, you know roughly like that gravity should scale like inverse radius or inverse distance squared, but you don't know what the constants are. So you're just guessing, right? So like you train an astronaut for like a year, you build a rocket for a year, and then you get 6 for the the gravitational constant, and then you launch it, and then the rocket missed, and then the astronaut unfortunately is no more. So you have to do it again. You have to train another astronaut for a year, build another rocket for a year, and then you get 7 for the gravitational constant. And unfortunately, it's still wrong. And so you just keep doing this until you finally get accurate enough with the gravitational constant that you actually land on the moon. If Newton actually was in this timeline, of course, you will know that gravitation is universal. So instead of doing this thing where you, give me a second. Yeah, instead of doing this thing where you just do trial and error and try to launch a rocket to land on the moon, you can just measure the gravitational constant on Earth because gravitation is universal. You can just kind of measure like, what the gravitation force of the apple on the apple is due to Earth. And then you can extrapolate, right, to get the right equations to get on the moon. Okay, so now let's come back to 2023. And like your OpenAI, you try to, instead of trying to launch a rocket to the moon, you're trying to train these giant, transformer models that can, you can chat with and whatnot, and hopefully can do math. Well, just like in this space program, where you have to train your astronaut and build the rocket over spans of months to years, you also have many training runs. So these are attempts to train your model. And when you launch a training run, this can take on the order of months. I say 3 to 12 months. I think GPT-4, for example, something like 6 months of pre-training, and then like there's another few months of kind of fine-tuning the model and investigating the model. But as you can see, it's a very like time-consuming and labor-intensive endeavor. And in this analogy with the space program, these numbers that we were guessing, these gravitation constants we're guessing, are analogous to hyperparameters, which are like learning rate, momentum, initialization. If you know what they are, if you don't, just think of like certain choices of how you design your training procedure that needs to be fixed before the training. And and so the gist of what I'm going to talk about today is that just like Newton said, gravitation is universal, and you can measure the gravitation constant on the Earth, and that will be enough to extrapolate to how to launch a rocket to the moon. Similarly, for training these large neural networks, beforehand, it really is a black box where this looks like quixotic to guess these gravitation constants and launch these rockets to the moon. But really, in real life, these teams at OpenAI, at Google, that are training these models are really doing something like this. They're just guessing these numbers and try to just be lucky and land on a superhuman AI. And the lesson I'm gonna talk about here is that just like Newton said, gravitation is universal. You can also understand that hyperparameters the optimal hyperparameters, like these learning rates and whatnot, are going to be universal, so that there's a way to measure these numbers on a small model and be able to extrapolate to the large model that you finally want to train. So at the end of the day, like the technique that's underlying this is in short called maximal update parameterization, abbreviated MUP. And let me know that this is something you can play with today. If you if you use PyTorch, you can do pip install MUP. But in short, it's just a principal way of scaling initialization and learning rate with the width of the model backed by some beautiful mathematics. I'm not going to flash you a table right now. This might look kind of complicated, but the point is just that this little table essentially encapsulates what MUP is and tells you how to kind of measure this gravitation constant on Earth and be able to extrapolate to gravitation on different planets, so to speak. But I'll come back to this table later. Don't worry about this right now. But the point is just that it's really a simple idea at the very end of the day. So the key thing we really like about MUP is it has these two properties called hyperparameter stability and larger is better. So as a way to explain this, it helps to first talk about a negative example. So if you look at how things are done today, which I'll just call that standard parameterization, then you can do the following experiment. So you can look at a hyperparameter on the x-axis. So you can look at, for example, learning rate, how fast you're taking gradient steps. You can look at initialization. If you don't know what these things are, just think about like say gravitation constant. And then on y-axis you can plot the training performance of the neural network. And again, if you don't know what that is, just think about like how close or how far you get to the moon when you launch your rocket. And when you do when you sweep over the hyperparameter and you do the experiment where you measure the training performance versus a hyperparameter, you typically see something like this, like a roughly convex shape where like there's like optimal zone where the hyperparameter should be. But if you try to increase the model size and repeat the experiment, you'll see like this kind of phenomenon where as you increase the model size, like like most of the time, like the performance increases as you increase the model size, but you see two very bad things happening. One is the shifting of the optimal hyperparameters. So you cannot just use the same number you get from the smallest model and use it on the largest model. And secondly, when you increase the model, fixing the hyperparameter, you can see that like the performance increases up to some point and then it decreases again, right? So these two phenomena are the opposite of what you want, which is stability hyperparameters and larger is better property. On the other hand, if you look at the maximal update parameterization, this table I showed you earlier, which tells you how to extrapolate these hyperparameters, then you can see that the optimal hyperparameters are stable as you increase the model size, and you always gain something when you increase the model size, right? So you don't have this kind of crossing of curves here, and again, like you always gain something when you increase the model size. So this is a cartoon that tries to give you the gist of the picture, but I'll give you this one slide that shows that in real life and really over many scenarios, the real life picture is very similar. So I don't know if you understand what transformers are or atom is, but just understand that this is a very kind of standard and typical and natural example of training. And here I'm measuring like training loss, so lower is better here. And on the x-axis, I have learning rate, which is a representative hyperparameter. And again, what you notice here is that the optimal learning rate, which is where the dips are in these curves, they're shifting to the left as you increase the model size in the standard practice. But if you look at picture on the right, which is using this maximal update parameterization with MUP, you can see that like the optimal learning rate is stable as you increase the model size. And of course, like the best performance on the right is better than the best performance on the left. So based on this understanding of this, hyperparameter stability property and the larger is better property, you can just, design a very simple algorithm to tune these hyperparameters for these large neural networks. Again, like the task, if you want to make the analogy again to landing on the moon, the task is to understand gravitation enough that you can plan ahead accurately the trajectory of the rocket. And similarly here, like the task is to understand the behavior of these large neural networks enough that you can plan ahead for the optimal learning rate, optimal initialization, so that you can get the optimal performance at the end of training. So here, each of these large models take, tens of millions up to even hundreds of millions of dollars to train a single neural network, which is still cheaper than, like building a space program back in the day, which costed billions of dollars. But still, these are very expensive endeavors. And so you cannot just, test directly, on the large model. Like in the exotic example earlier, we are just sending rockets to the moon until we get the gravitation constant correct. Like this is not feasible. So instead of doing this, you in this algorithm called muTransfer, you just shrink the model, tune the small model, and then transfer the optimal hyperparameters back to the large model, right? So this is kind of like analogous to measuring the gravitation constant, on objects on the Earth. And if you measure it accurate enough, then that also extrapolates to planning a trajectory of the moon.
Well, pre-processing, you already new variance. How do you keep it stable? That's what I'm saying. You know already. That's a good and a bad side, I would say, because it's like when it's fixed, that means like it must be in a kind of an optimal state.
Yeah, it turns out this is a free lunch.
What I mean is like before you start the process, you already have fixed. I mean, you have already done some free.
Yeah. So okay. So first of all, like just so I can phrase my answer at the right level, like how familiar are you with deep learning? Okay. So the way like these things work is so first, do you understand like how gradient descent works? Okay, great. So the way these modern like neural network training works is that you start with a network with like no information at all about data, and the way you do that is you kind of randomly sample the weights from some random Gaussian or whatnot, some random distribution, and then you start training. Okay, and like roughly speaking, there are like two groups of like most important hyperparameters to choose for this whole training procedure. One is where you start. And so usually that means like what is the distribution you're sampling your weights from? And in particular, like what's the variance of the weights, right? So if you can sample IID or entries from a uniform or something, but like how large should it be, right? So like that's one number for like every weight matrix in the network, for example. And then the second group that's very important is the learning rate. So like when you take a gradient step, how large, what's the number you multiply that step by, right? And so these are the two groups of numbers that like probably the most important groups of number that determine how your training run is going to go. I mean, there are also other ones like how long should you train, but like just fix like say like we train for like 10 trillion steps. Let's fix that. But let's just think about like what's the learning rate and what's the initialization. Okay, and so I'll get to that later. But like essentially the question here is that when you say double the number of neurons to your network, how should you scale these numbers? Like what is the natural unit to this, for example? And you can imagine multiple ways of scaling that can give you different behaviors. And it's not a priori is not very clear like what's the right way of scaling. Versus, I mean, so it's kind of like if you're Newton back in the day, or I mean even Newton's day, but like, say today, like if you want to express the law of gravitation, you need to choose your units correctly. And if you don't choose your units correctly, then like when your distance get longer, you need to adjust your constants by a commensurate amount. But by like when we talk about gravitation, like the reason these 6.674 is a constant is because we chose the units correctly. If we don't choose the unit, we choose a unit that like kind of varies with distance or something like that, then this constant, the gravitation constant, is not a constant. Does that make sense? Yeah.
Just based on the best people analogy, you can find many future videos that say like if you double your network width, you can multiply your early recipe. And it's, this is like a recipe. It's not an exact recipe. And so much salt. But Greg's kind of saying that if you set things up right, there's no need to do.
Okay, let's move on. So just to give you a sense of like how universal this law of gravitation really is, like in our work, we tested across a really wide range of models. So like I'm putting some words to paper on this slides, but probably if you are not in machine learning, you don't know what these mean. But roughly speaking, like I can tell you about like the scale of these things. So on the largest scale, there's 6.7 billion parameters. And that's not even like large by today's standard. And the MLP on CFAR10 is maybe like 10 million, 1 million parameters, something like that. So it's a very wide-ranging scale of models. And in general, what you can find through these experiments is two things. One is that when you look at larger and larger models, the improvement of what I just talked about, like this muTransfer technique, is bigger and bigger compared to prior state of the art, where people kind of tune the neural networks by hand, like kind of guess those numbers. And like a priori, this is kind of counterintuitive because in general, in engineering sciences, you expect that, it's harder to improve a better model by 1% than like a worse model by 1%. Like it's really hard to improve a 99% accurate model by 1% than like a 50% model by 1%. But here you have the entire reverse of this. Like the better model actually improves more. I mean, of course, like this is like nowhere near 99%, but like we're improving something like 80% by 1%, or 80% by 2% versus like 50% by 0.5% or something like that, which is really counterintuitive if you think about it. But really, at the end of the day, what this really says is that this is a free lunch. Like just people were just really bad at guessing these hyperparameters. Just like we're guessing gravitational constants when we're launching rockets to the moon, and just like the low-hanging fruit is more and more enormous as the model size gets bigger, just because as the model size gets bigger, people get worse and worse at guessing these numbers. And secondly, like the practical aspect of this is that when your model gets larger and larger, the total tuning cost as a fraction of the training cost of the large model becomes less. It vanishes to zero. And this is just because like when you it's kind of like when you try to measure gravitational constant, you can measure it on like some object falling on Earth. You don't have to build a rocket to the moon or something. So like this, measuring like the acceleration of the apple, the cost of that compared to measuring the cost of building a rocket and training astronauts, it's a very minuscule cost. And just for some concrete numbers, like for this experiment where we collaborate with OpenAI and try to transfer hyperparameters from 40 million parameters to 6.7 billion parameters, the end result is that we effectively doubled the model size in terms of quality. So like this 6.7 billion parameter model is like after tuning it with muTransfer is about the same quality as the 13 billion parameter model. And the total tuning cost is only 7%. So it's rather getting to the negligible territory. So like we're essentially getting all of this performance for free. And it's totally one of those free lunches that comes once in a while, an arbitrage opportunity. Okay, so that's like roughly a summary of the properties, like on the relatively speaking, the practical side that we really like. And so the goal now is to kind of give you a taste of, well, first of all, I didn't really explain what muP is, so I want to explain that. But probably if people aren't that familiar with deep learning, I'm just going to give you a very evocative example to give you kind of the sense of mathematics underlying this. But feel free to ask questions. Okay, so now let's just forget about everything I've said. Forget about deep learning, and this is just a mathematical puzzle. So like like be on alert. I'm gonna call out random names. Okay, so the puzzle is the following. So I have n random numbers, sample independent ID, so independent and identically distributed from a standard Gaussian distribution. And then let me define this random variable Zn of C, just as, so C here is a real number, and I set this to be C times the sum of these random variables. Okay, and then I define, a loss function, or if you're from physics, an energy function, which is like this, double wall thing. But like the specific doesn't really matter. But let's just take this double wall as an example. And then like what I care about is what is the optimal C, this number here, that minimizes the expected energy or loss of this random variable. Okay. So forget about deep learning. This is like entirely self-contained mathematical example. Now my question is, how does C star n scale with n in this example? Yeah, okay, great. So essentially, yeah, it's essential limit kind of dynamics, right? Because if you think about it, the each of these random variables, when you sum them up, the variance scales like linearly, the variance scales linearly in n. So the standard deviation scales like square root of n. So like roughly speaking, if you want to, like when n becomes large, like the minimizer of this guy like must be something, in a constant range, right? So to make it in a constant range, C must scale inversely according to square root of n, right? So like at the end of the day, you have something like 1 over square root of n. I mean, it turns out it's exactly 1 over square root of n just because I set the numbers up so that it is so. But the point here is the scaling, right? And so if you can graphically represent this as this kind of like light cone plot or whatever, but if you plot like C star in log scale on the x-axis and n on the log scale on the y-axis, then like it's roughly something like this, like array like this, where if you double the width, then if you double n, then you should divide C star by square root of n, right? Okay, so round 2. So good job. What's your name again? Ogre? Okay, round of applause. Round of applause. Okay, so round 2. So he cannot answer. Somebody else must answer. Okay. Okay, so round 2. Now, like the W1 to Wn, you sample from a Gaussian with mean 1 and variance. But otherwise, the same definition. Okay, now how does C star scale? Same? But 1 over root n? Oh, that's incorrect. 1 over n? Yeah, okay. Yeah, so round of applause. Well, I mean, so the reasoning here is the following, right? I mean, like it might help first to like assume like the variance 1 here, suppose it's 0. Then like these numbers are just ones. Like they're exactly ones. So like, Z n C is a deterministic number that just equal to C times n. So again, if you want to minimize this energy function that is fixed as n goes to infinity, the input better be in a constant range. So the natural way to scale this is to scale inversely to n. So you get something like this, something proportional to 1 over n. I mean, in the general case, when you have variance here, this is a law large number behavior where when you sum up a lot of random variables and you divide by their number, so you're taking their average, right? Then by law large numbers, we understand the fluctuation will decrease and vanish to 0 as the number becomes large. Just our normal intuition of averaging a lot of noisy things decreases the noise, right? Okay, so again, you can graphically represent this by this array going up and to the left, but more to the left than the 1 over square root of n, right? So this is kind of like these examples are a very typical illustration of like the really kind of coarse behaviors that happen when we have a lot of things interacting together in a large system. Like 1 over square root of n, 1 over n are kind of 2 typical x powers of n that appear in these contexts. Okay, so round 3. Okay. So now we have 2 sets of these numbers, W and V. So like the first set look like the first set with 0 mean, and the second set look like the second set with mean 1. And then like this random variable is gonna be Well, so first of all, C is now two numbers, the C1 and C2. And then the Z random variable is the max of the things we've seen just now. Now the question is, how does C star end where now C star is two numbers, one for C1 and one for C2? So how do they scale as n becomes large? So exactly. So when you combine, like these different Z's, right, from different cases, as long as a function of combination is like something that doesn't depend on n, then you can expect that, like you would reduce to the component scaling, right? So, all right. So again, this is like entirely self-contained mathematical example to, pick your intuition about how things scale. But, coming back to the neural network world, we can intuit things like the following. So this is roughly analogous to what actually happens in a neural network, where these W1 to Wn, they're like the weights of the neural network, which are kind of connections, the strength of connection between neurons. And then N here is the width of the network, which essentially means the number of neurons here. And, in this third example where we had different, sets of W's and V's, like these W's and these V's can be thought of as coming from different parts of the neural network, like different layers of the neural network, for example. And these C's that we're looking at, they correspond to things like learning rate and initialization, in other words, hyperparameters. So, and these are the things that we care about. These are analogous to the gravitational constant that we saw earlier. And then these Z random variables are roughly speaking like corresponding to the training result of the network at the end of training. And this F function is roughly speaking like a measure of how bad the model is. So you want to minimize this badness function. And finally, like the C star is the optimal hyperparameter, right? That minimizes this badness score across the randomness. And this is what we're interested in. Like, how does the optimal hyperparameter scale as you increase the network size? N here is the width network, and it's like a very typical notion of model size. And for example, like in, GPT-3, like N is roughly on the order of 10,000. So, not small, but like also not like super humongous. Okay, so hopefully this makes sense and nobody is too embarrassed by this example. But let's come back to this table at the very beginning of this talk that I fast you this table, but I skipped over the explanations. So again, I won't be able to really go into details about this, but let me try to explain what this table shows. So on the rows are the different hyperparameters that we kind of have encountered already. So like initialization variance is like how large you should sample your weights. The learning rate, so the two rows here are learning rates. And they are for different algorithms. One is for stochastic gradient descent, another one is for ADAM, which is like advanced version of optimizer used in deep learning. If you don't understand what ADAM is, don't worry about it, just ignore this row. And again, like these, like we're interested in the C star of N behavior of these hyperparameters. So we want to know when N, which is the number of neurons in the network, increases, how should we scale these hyperparameters in the rows? So in the columns, we have different parts of the neural network. So you have like, weights of the input layer, weights of the output layer, weights of the hidden layer, so different parts of the neural network. And then depending on which part of the network it is, you have different ways of scaling, different rules of scaling the hyperparameters in the rows. So yeah, so there's, a lot of expression here with color, but don't worry too much about it. Like only just read the purple plus black text. That is what MuP is about. And I mean, as you can see here, like the expressions are either like some power of fan in or some power of fan out. And fan in and fan out are just notions of width. Like roughly like the number of neurons going into a layer is the fan in, and the number of neurons going out of that layer is fan out. So it's different notions of like number of neurons in a layer. And just like before we had these powers of n, here we also have powers of fan in or powers of fan out. Okay. Now I won't have the opportunity to really explain like the precise mathematics behind this, but hopefully like this example gave you some sense of like what we're dealing with here. Of course, it gets far more complicated once you put in like the nonlinear structure of neural networks and like the hidden way matrices, which are like kind of large square matrices. But again, like at the end of the day, you just have to deal very carefully about central limit style effects and the law of large number style effects. Okay, so but let's see. So I have like 9 minutes, but I guess we should wrap up 5 before. So let me 4 minutes, yeah. So okay, let me kind of quickly give you an idea of the real mathematics behind this and like with the kind of like highbrow mathematics that might be involved here. But again, like the picture here is that you have this large neural network with many layers, for example, and as a result, you have a lot of different hyperparameters here. Like I mean, here we have initialization and SGD learning rate, but you can have like one of these two numbers for every layer of the network. So when you have many layers, you just have a lot of numbers to deal with. And the question is, how do you scale this large array of numbers as you increase the model size, right? And a priori, like there are many ways to do it. And any way you fill this table, where each entry is like a power fan in or power fan out, it's a particular way of scaling the neural network. And like a priori, you don't really know like what's the right thing to do. So earlier we saw pictures where like we look at rays going to infinity, and in general like you have a similar kind of picture where the x-axis which is really a high dimensional space, which can be like again learning rate initialization for every layer, so it's a large dimensional space, but each kind of like scaling gives you a kind of flow of these hyperparameters toward larger and larger width. So each kind of flow is roughly corresponding to a direction to infinity. So like mu-p, the hero of this talk, might be represented in one picture like this flow to the upper left, and then the standard parameterization may be like a flow directly up. But the point is that like the parameterization is a slope, not the intercept. So as a result, you can, under this kind of intuition, you can think of like, okay, I have a chunk of hyperparameters for a model of size with 100. What happens if I try to flow this chunk of hyperparameters toward larger and larger width, but under different kind of flows? So, for example, in the standard parameterization limit, which is a standard practice right now, like, in this kind of way of representing the picture, the flow might be directly up. And then if you flow according to mu-p, you get some kind of limiting behavior of the network. And then if you flow according to another thing I haven't mentioned before called neurotangent kernel, then you're going to get a different kind of behavior. And obviously, there are like infinite number of possibilities here. And so here, like, what you can notice is that a different kind of flow result in a different kind of behavior in the infinite width case, in the infinite width limit of the neural network. So the analogy here is, you follow like the slope of the flow is bijective with the behavior when you follow the slope to the end. Yeah. So like as concrete examples, right? Like we know that from central limit theorem that if you scale your like ID sum of the zero mean random variables with a scaling 1 over square root of n, then you're going to get a constant sized Gaussian random variable in the limit. And similarly, when you scale a sum of ID random variables with a non-zero mean, with a scaling of 1 over n, you get a deterministic number, non-zero number at the end of this scaling. So roughly speaking, this is like, this gives you a sense of like, the bijection between parameterization and infinite width neural networks in terms of like normal, things in probability that we know about, like, central limit behavior or larger number behavior.
Thanks heaps. Also, I feel very bad that we kind of truncated what is very fascinating stuff. So we will have another session at some point to be announced. And so let's thank Greg again.